Hello, today I'll be presenting my final year project titled Object Detection for Autonomous Vehicle. The three main questions that will be addressed in this presentation are: what is object detection? Why is it important for autonomous vehicle? And lastly, how does object detection algorithm work? First of all, what is object detection? Object detection is a computer vision problem that deals with locating and classifying objects of interest in the environment. Object detection algorithms are separated into two categories, namely 2D and 3D algorithms. In the video shown, it is a 2D object detection algorithm being run. 2D object detection locates the object by putting a 2D bounding box around it and providing a confidence score for classification. Next, we will see an example of the outputs of 3D object detection algorithm. 3D object detection algorithm tackles the problem on how to put 3D bounding boxes on the objects of interest. 3D bounding boxes provide an accurate spatial representation of the object in reality and can even provide information regarding the pose of the detected object. Why is object detection important for autonomous vehicle? Let's have a look into an autonomous vehicle system to find out. An autonomous vehicle system is commonly divided into three main modules, namely perception, planning, and control. The perception module of an autonomous vehicle is tasked on building an accurate representation of its surrounding environment and localization, which is figuring out its location. The planning module uses information regarding the environment and the location of the autonomous vehicle from the perception module to decide on navigation actions to take to reach a desirable destination. Once the navigation plan is decided, the control module is tasked with interfacing with the actuators to steer and move the vehicle according to the planned actions using a control algorithm. Thus, the main focus of this project is in the perception module, mainly in researching and deploying object detection algorithm. Object detection is vital for the safety of an autonomous vehicle navigating around an environment, as many control decisions relies on detecting different objects of interest in the surrounding environment. For example, a self-driving car has to decelerate to a stop when a red traffic light is detected within a certain distance in front of it, or else a crash is bound to happen. These planning and control actions relies on information from the 2D object detection algorithm to detect and classify the state of the traffic light. In this project, we are interested in utilizing object detection algorithms to solve challenges from the RobotX maritime competition, such as executing different planning and control action according to different shapes and totems detected in the environment. The RobotX maritime competition for this year has unfortunately been cancelled. However, I have shown a proof of concept of a working 2D object detection algorithm on RobotX images. How does object detection algorithm work? To understand how object detection works, we first have to understand neural networks and then look into a variant of neural network named convolutional neural network that is well suited for feature extractions on images. And finally, we'll look into state-of-the-art 2D and 3D object detection algorithms. Firstly, what are neural networks? Looking at the visualization, it is showing the first and simplest type of artificial neural network device, the feed-forward neural network. It is feed-forward as information propagates only in the forward direction from the input nodes to the output nodes. The key thing to understand about neural network is the ability of it to approximate the continuous function that represents the relationship of the input data to the output prediction. Neural networks are referred to as universal approximators. The neural network learns from data by optimizing the loss function. Therefore, neural network does not require us to manually code the relationship between the input to the output, which is why it is so useful for tasks with extremely complex relationship between the input and the output. Neural networks can be summarized as a concatenation of a multitude of parameterized transformations such as linear mapping and nonlinear mapping. There are a few key components to the inner workings of neural networks, one of them being forward propagation. Forward propagation is the process of the input values being propagated through the neural network to the output layers by putting values of weights and biases through linear and nonlinear functions. The linear function used is a very familiar mathematical equation, y equals mx plus c, but in this case the input x multiplies the value of the weight parameter w, and the y-intercept in this case is known as the bias parameter. To add nonlinearity to the network, nonlinear functions, commonly referred to as activation functions, are used. Two very common activation functions in neural network are sigmoid and ReLU functions. After forward propagation, the output prediction value y hat will be compared to the ground truth data y to find the error value. This is done using a loss function. A very simple loss function is the mean square error. Once we compute the loss, we can optimize the loss function. This is where the learning part of the neural network is being done. How is the loss function optimized? The loss functions are optimized using a technique called gradient descent. As of its name, it is literally a process of descending the loss function utilizing gradient values in search for the minimum point. We can think of this as the neural network finding the points with the least amount of error by subtracting the tunable parameter by its gradient. The gradient of the parameter is computed with respect to the loss function. The gradients are computed using a process called backpropagation. Backpropagation computes the partial derivative of the weight and bias parameter with respect to the loss function, which can be computed using the chain rule. Therefore, through the process of forward propagating to get the output value and taking the output value into a loss function and then optimizing the loss function using gradient descent, the neural network is able to learn through many iterations and data to find values of weights and biases that can provide us with very low error. Feed-forward neural network can even be used for classification. For example, I implemented a feed-forward neural network classifier from scratch in Python to classify my favorite food, char kway teow, from everything else. You can imagine that it will be tremendously difficult for programmers to manually code up the necessary functions that can take in flattened pixel values as the inputs and output the expected classification. However, with neural networks, it can learn the function through data. However, using feed-forward neural networks on images is not the best idea, as spatial information on images are essential. A much better way to extract features from images is by using convolutional neural network, abbreviated as CNN. CNN is a variation of neural network that is great for features extraction for images. CNN uses nearly all the same operation as mentioned for neural network, with a few new operations introduced to learn spatial hierarchies of features through filter kernels. CNN architectures are set up in a way where we do not need to flatten the images into a 1D vector, but can remain the image structure as it is. The learnable parameters are set up in the form of a filter kernel matrix, which is used for convolutions. Convolution operations involve sliding a filter kernel matrix across the image in a sliding window fashion. The main goal of the CNN is to learn unique filter kernel matrix value to extract out features of the image. A filter kernel matrix is usually of an odd size of 3 by 3 or 5 by 5. But what's so special about filter kernels? For example, if we were to run the two simple 3 by 3 filter kernel matrix shown across an image, we can emphasize the edges of the image. The kernel filter Gx are emphasizing vertical edges, while the filter kernel Gy is emphasizing horizontal edges by using sharp change in the intensity as we go across the image. Gx and Gy are known as Sobel operators. Utilizing the Sobel operators, we can do edge detection. This is an example of using the previous two matrix Gx and Gy to extract out edges in an image. CNN is very powerful because it can learn hundreds of unique filter kernels that can extract out different features from an image. Using CNN for my classification project, the accuracy went up from 76% to 88%. In conclusion, CNN is very useful in extracting out features from images. Therefore, CNN is widely used in computer vision tasks ranging from segmentation, generating synthetic images, classification, and most importantly for our project, object detection. An example of a state-of-the-art 2D object detection algorithm is You Only Look Once, YOLO. YOLO was revolutionary to the 2D object detection field because it framed the 2D object detection problem as a regression problem in a monolithic network. YOLO is of interest in this project as it has real-time performance with good accuracy results. The regression parameters for YOLO is the x-coordinate, y-coordinate, width and length of the bounding box, and an object score that determines whether is it an object present or absent. And lastly, the class probabilities of our objects of interest for the purpose of classification. CNN is used as the backbone network for 2D object detection algorithms. Backbone networks are used for features extraction. Thus, it is worth noting that if we use CNN architectures with higher performance, we will possibly improve the performance of the 2D object detector. YOLO splits up an image into grid cells. Each grid cell will consist of 5 proposed bounding boxes of different size. From all of the bounding box proposed, which can be up to 1,000 of boxes, YOLO searches for the bounding box coordinate, size, and class probability that it is closest to the ground truth. To implement the 2D object detection algorithm, we first have to collect images. Next, we can do data augmentation on the images to increase the diversity of the dataset. We then need to label our images and split the dataset into training, validation, and testing. Finally, we can train the network. However, in most cases, we do not need to train a network from scratch as it can be very time-consuming. We can instead use a pre-trained network and retrain the last few layers. This is a process known as transfer learning. I've implemented the 2D object detection algorithm for the RobotX team using the TensorFlow Object Detection API. A pipeline with the TensorFlow Object Detection API was set up so that future RobotX member can add their own images, label them, and use the script that has been written to retrain the network and test out the object detection algorithm. In this project, 3D object detection algorithms are also of interest. 3D object detection is very important as 2D object detection is insufficient for autonomous vehicle application. Autonomous vehicle application requires accurate spatial information for safe navigation. Autonomous vehicles are commonly equipped with camera and LiDAR sensors, as seen in the 3D model of the RobotX autonomous vessel on the left and a self-driving car setup on the right. The research community has proposed many different methods. There are methods that uses only camera, methods that uses only LiDAR, and lastly, methods that fuse both LiDAR and camera data. For each method, there are a great variety of unique data pre-processing techniques and network architectures that has been proposed. For this presentation, I will be introducing a 3D object detection method that uses only LiDAR, called Complex YOLO. Complex YOLO pre-processes LiDAR point cloud data into a 2D bird-eye view RGB map. The RGB map is split into grid cells. Each grid cell is encoded by taking the maximum height of the point cloud, the maximum intensity, and the normalized density of all the point clouds within the grid cell. Then, 2D object detection algorithms such as YOLO will be applied to regress 2D bounding boxes. The 2D bounding box are extended into the 3D space for the object using a predefined height of the object. An extra regression term which is needed is the pose of the object are parameterized using complex angle in this algorithm. After training the complex YOLO algorithm on a very common self-driving car dataset called Kitty, we can visualize some of the test results as follows. The top part of the image is from the front view camera, and the bottom part is the bird's-eye view created from LiDAR point clouds. To summarize, we have gone through how neural networks can learn from data, and then we look into a variation of neural network called convolutional neural network that is more suited for the image domain as it learns filter kernel values. Building on convolutional neural network, we then show a 2D object detection algorithm. Lastly, we look into a 3D object detection algorithm that relied on 2D object detection. It is worth noting that there are few more different 2D and 3D algorithms that has been explored in this project, but not shared in this presentation. The future research direction of this project will be looking into investigating more 3D object detection methods in search for good performing real-time methods. Next, we will also need to figure out how to characterize the uncertainty in neural networks prediction. This is very important for autonomous vehicle applications such as localization and mapping. Lastly, we can also look into object tracking. The projects mentioned in this presentation can be found over at my GitHub. Thank you very much for listening, and if you have any question, please feel free to leave a comment.